This week we're going to discuss an application of magnetic resonance that is dear to chemists and biochemists alike, but also has some applications in biomedical imaging. And I want to first start out with some examples on distinguishing that illustrate the distinction of the magnetic resonance signal based on its chemical environment. And the prominent example in magnetic resonance imaging here is fat and water. So if we take an image of the brain, here are the eyeballs. This is a transversal cut. Here's the midline. This is a typical T1 weighted image here. And then here the same image has been repeated, but through some manipulations, the signal that arises from the fat has been eliminated. And we will discuss how this is being done. So we see the subcutaneous fat is gone, but we also see that the signal behind the eyeballs here is eliminated. And this is due to the fact that we have behind our eyeballs, we have the so-called retrobulbar fat. So in this image, one has been able to eliminate the source of signal from due to fat taking a particular property. And so this bright region here, which could potentially be a tumor, is established here as containing a lot of fat and is most likely a lipoma. So if we look at the body, then we have the original image, which is everything included. Then one can generate an image that has only the fat signal. We see the fat signal here on the surface. That's this fat here, or just the water only signal. Or here another example of somebody who carries more fat. There is more fat here in this image as illustrated here in the fat only image, and in the water only image, the area which is rich in fat is not so intense. Here's another example. This is MRI of the breast. We have a normal MRI of the breast here, very bright images, and then to distinguish between potential cancerous tissue and fat signal, which both would give up in these type of images a bright signal. The signal here was acquired with suppressing the signal from the fat, and one sees a bright signal here, which is a potential cancerous lesion. Here it's important to note that cancer typically does not contain a lot of fat signal. Here's an example from fatty liver. This is an area taken here from the liver, and one looks at now the signal. The water in these different cases of fatty liver is constant, and here on the side, this extra peak here goes from mild to moderate to severe fatty liver. So this is an example of the way the data is analyzed to obtain biochemical information in vivo. So why is NMR spectroscopy so important for chemists and biochemists alike? It is actually so important that essentially any department of biochemistry or chemistry does have its NMR equipment. And the reason here is it is a routine tool. It allows non-destructive analysis of samples. A more amusing example is, for example, to analyze the quality of wine in bottles. If you have an expensive wine, but you want to have quality assurance that this wine really is what it pretends to be, this can be done. You don't want to open the bottle of wine. Another example is if you have spent several years in synthesizing a new compound and you want to verify that the synthesis process has properly worked, and you have only a few milligrams of the compound that has been synthesized, you don't want to subject it to an analysis that's destructive, that destroys the molecules. Other examples include structure determination in solution. So since we are limited to soluble molecules, this allows to study the molecule's structure in solution. Molecule dynamics are accessible since we have T1, T2 and similar effects, and also chemical reactions can be followed in situ. So how is this done? Well, typically the solution with the compound is put into an Eppendorf. One needs a strong magnetic field, just like with biomedical applications. Here the z-axis is vertically, that is a vertical bore NMR instrument. The sample is inserted, data is obtained, the data is analyzed, and here's an example from this complex molecule, and one now looks at different signals from this molecule, each corresponding to a different proton in the molecule. Or more complex here is the signal of protons. This is a two-dimensional plot showing what signals are linked to other signals here. I will come to that later. This typical data can be analyzed, and from that the structure can be determined. So here is the structure of a protein. One can see the core and 4 alpha helices here. Here's another example of a structure that's being determined with NMR. This work was pioneered by Kurt Wüthrich, a biophysicist from Zurich, who for his work received the Nobel Prize in Chemistry in 2002. So, first, before I come to the chemical effects of how we can measure chemistry with a nuclear phenomenon, that is nuclear magnetic resonance, I want to dwell into a bit on the effect of the relaxation on the magnetization. So let's look at the effect of T1 and T2 on the signal. We have here time. We apply an RF pulse with flip angle alpha. The flip angle for such an RF pulse is given by gamma B1 times its duration tau. And so the magnetization mz after this RF pulse is given by the magnetization, C magnetization before the RF pulse times cosine alpha. The transverse magnetization after the RF pulse, that would be here, is given by the Z magnetization before the RF pulse times sine alpha. So here this is the transverse magnetization at this time point, which we'll call mxy of 0. So these are the effects of T1 and T2 on the signal, are given by the transverse magnetization evolves now by this initial transverse magnetization with its exponential decay. That's what we see here. And so after the RF pulse, the signal decays under the influence of T2 relaxation. Now if we call this the Z magnetization at time 0, then this period before the RF pulse, which we typically call the repetition time, TR, or TI, the time of inversion. We'll see shortly why this is called this way. During this time, we have the influence of T1 relaxation. So the effect of T1 is given by this differential equation, the solution of which is given by this general equation here. And we call this equation also longitudinal coherence, and we'll see shortly why. So if we set in mz of 0 is equals to this term here, then we substitute here the solution. We substitute this term in here, and we obtain this solution here. Now, longitudinal coherence, we call this longitudinal coherence because the effect of T1 on the signal, ultimately, because we ultimately obtain an mz of t, the mz of t is by the RF pulse is converted to transverse magnetization, which is being detected. So the influence of T1 depends on prior RF manipulations. And this comes from, in the solution to our differential equation, from this term here, which includes prior manipulations, that is prior applications of RF pulses, that is B1 fields, that have been done to the magnetization. So this is important here, that what we do to the magnetization in terms of RF pulses, that influences on how T1 manifests itself on the signal. So now I want to address the question, under what optimal conditions are we most sensitive to changes in T1? This is also the flip side of that, is under what optimal conditions can one measure the influence of T1? And here the term to introduce is inversion recovery, and you'll see shortly why it is called inversion recovery. So essentially what we're looking at is a application of 2 RF pulses. It's the multipulse experiment, and it is the traditional experiment which is used to measure the influence of T1. So we'll consider here an RF pulse of flip angle alpha, a certain time delay tau, and then a 90-degree pulse. This time here we will call TI, or time after inversion. This 90-degree pulse, pi-half pulse, its sole function in this particular multipulse experiment is to convert the Z magnetization, which is present right here, into transverse magnetization because we want to measure the Z magnetization. And the Z magnetization cannot be directly measured, so one has to go through the detour of converting it into transverse magnetization. So that is the multipulse experiment we are going to consider. So the measured signal is essentially the Z magnetization after this time period, Ti. This Z magnetization is given here by the solution of the differential equation. We'll rehash it, and here we have mz of 0. mz of 0 is equals to m0 times cosine alpha. So we have waited a long time. We have equilibrium magnetization here. We apply an RF pulse alpha, and so the Z magnetization at this time here is m0 times cosine alpha. And we substitute this term here into this term, and this gives us this equation here, where we express now the Z magnetization as a function of this time Ti here. Now, two things. What is the best choice of alpha? So what would allow us to produce the most sensitive experiment to changes in T1? We'll use the same approach that we discussed last week. We introduced in the first lecture in the first part of the course. It's the error propagation calculation. So first we're interested in establishing how sensitive is our Z magnetization right here at this point, just before the pi-half pulse, to changes in T1. That is, we calculate the derivative of the Z magnetization with respect to T1. This gives us this expression here. Here's the Z magnetization. We'll take the derivative of this with T1, and here we have not put Ti, we've just put the time T, and we'll call this function f. Now we want to know when, under what choice of alpha is this function maximal. So we'll take the derivative of this function with respect to alpha, and we'll set that derivative to 0. This tells us at what point with respect to alpha is this function maximal. And here's the derivative. This is non-zero, this is non-zero, so we are interested in a solution where sine alpha is equals to 0. And here we have two possibilities. The alpha is equals to 0, or alpha is equals to pi. Now alpha equals 0 is a silly experiment, because then it's basically saying we're not applying this RF pulse. The flip angle is 0. We would be just measuring equilibrium magnetization, and we're not sensitive to T1. So the correct answer here is alpha equals pi. So alpha equals pi, that is a 180 degree pulse, or as we have introduced earlier 2 weeks ago, this is an inversion pulse, and hence this experiment is called inversion followed by recovery, and Ti is called time of inversion. So in this particular case, we have now the Z magnetization as a function of Ti is given by the equilibrium magnetization times E1 minus 2 times e to the minus Ti over T1. Next question is, what would be the proper choice of the time Ti here to detect changes in T1? So we want to choose the Ti such, we have established that alpha is 180 degrees, we want to choose Ti such that we are most sensitive to changes in T1. So we will take this function here, and we will calculate now the derivative of this function with respect to time. Here we did it with respect to alpha to find the optimal alpha. Now we'll do it with respect to this time t here, which is our Ti. This is the chain rule. We get this expression here. We simplify the terms. This is non-zero, this is 2, this is non-zero, so the term in the bracket has to be 0, and we're finding that the optimal inversion time Ti to be sensitive to changes in T1 is if we choose Ti equals T1. This is again not surprising. We have an exponential function, and again, in an exponential function, as you increase, you're not sensitive here, you're not sensitive here, somewhere in the middle, and it turns out that you're most sensitive exactly when this time equals to T1.